Lesson 7.3.4, Hypothesis Tests for a Population Proportion, Lesson 4. Introduction. In this lesson, we review the 4 steps of a hypothesis test and the errors that can be made in this decision-making process. We begin with a review of the process. Step 1. Determine the hypothesis. The null hypothesis, which is, we write it as H with a little 0, right? Assumes a value for the population proportion P. The alternative hypothesis, H sub A, states that P is greater than, less than, or not equal to this value. In the alternative hypothesis, less than inequalities indicate left-tailed tests, while greater than inequalities are for right-tailed tests. Not equal inequalities are two-tailed. Step 2, collect the data. Here we verify criteria for approximate normality and summarize data from representative samples. The criteria for approximate normality require that n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, using p from the null hypothesis. The summary statistics are the sample proportion and sample size, p hat and n. Step 3, assess the evidence. The z-score of the sample proportion is called the test statistic. To find this z-score, we use the mean and standard error of the underlying sampling distribution. To compute this, we continue to use p from the null hypothesis. So remember, the mean is p, and the standard error is given by the square root formula, p times 1 minus p divided by n. And remember, you get the p-value from the null hypothesis. The z-score is equal to p hat minus p divided by the sigma, right? The standard error from above. Once you do that, you find the p-value. The p-value is the probability of observing a test statistic that is at least as extreme as the one above. For right-tailed tests, the p-value is the area to the right of the test statistic. For left-tailed tests, the p-value is the area to its left. For two-tailed tests, the p-value is twice the area to the right of a positive test statistic or to the left of a negative test statistic. So you can use either one for a two-tailed test. You just remember to double it. Step 4, state a conclusion. We use the p-value to make a decision about the null hypothesis. If the p-value is less than or equal to alpha, the evidence is strong enough to lead us to reject the null hypothesis and support the alternative hypothesis. When the p-value is greater than alpha, the evidence is not strong enough to lead us to reject the null hypothesis. We do not reject the null hypothesis, so we do not accept the alternative hypothesis. Once the decision is made regarding the null and alternative hypothesis, it is important to conclude with a statement which summarizes what was learned in plain English. Explain what this means about the population of interest. So again, we're never okay with you writing as a final answer, we reject the null and support the alternative or something like that. You need to say it with respect to the problem, right? In the context of the situation. Using plain English as if you were explaining it to, your mom or something like that, right? So try these. In 2013, the U.S. Department of Defense changed a policy that affected women in the armed forces. Under the new rules, women who met physical requirements could be assigned to combat positions. Many people in the U.S. were opposed to that decision. About 18% of women were against it, and in January of that year, Gallup researchers claimed that the proportion for men was even higher. In a random sample of 256 U.S. men, 57 said they were opposed to allowing women to serve in combat positions. At 5% significance, use the steps above to test the claim that, in 2013, the proportion of men in the U.S. who were opposed to allowing women to serve in combat positions was higher than 18%. Okay, so we are going to go through this hypothesis test from the beginning. Again, this is our 4th lesson doing this, so hopefully by now this seems familiar. So we're going to start by determining the hypothesis. Remember, we have the null hypothesis, and we also have the alternative hypothesis. So the claim here, they're saying that the proportion of men in the U.S. who were opposed to allowing women to serve was higher than 18%. Higher means more, right? So that would be our alternative. P is bigger than 0.18. Okay, that is the alternative hypothesis. So the null hypothesis, remember, it's always an equal sign. Okay? So that's the null hypothesis. Step 2, collect the data. Okay, so let's first verify that this is normal, right? Verify that this is normal. So let's see. What was our sample? It says in a random sample, that's very good. So let's say sample is random. And let's also check that n times p and n times 1 minus p are both bigger than 10. So n times p would be, let's see, there were 256 men in the sample, and p is 0.18, right? We use the null hypothesis. So if I multiply 256 times 0.18, I end up with 46.08. And here, if I do 256 times 1 minus 0.18, I get 209.92. Both of these are bigger than 10. So this means the normality criteria is met. Okay, so next, let's go ahead and write down our p hat. Remember, p hat is the sample proportion, right? And so that's going to be how many men in the sample actually were opposed to allowing women to serve in combat positions. It says 57 out of 256. So I'm going to write 57 over 256, and let's see what that equals in our calculator. I get 0.22. I'm going to round it up because of the next number, so 223. Okay, so we have our p hat. Let's go to the next step. Well, actually, let's see here. Yeah, so I guess I just wanted to make sure I wasn't mixing up the steps. So that's everything we need for step 2. So step 3 is where we're going to list the mean, the standard error, the z-score, and the p-value. So let's start with the mean. Mu sub p hat is just p, which is 0.18. Okay. What about the standard error? The standard error is going to be the square root of p times 1 minus p divided by n, which in this case is the square root of 0.18 times 1 minus 0.18 divided by 256, right? So let me go ahead and do that in my calculator. I get 0.18 times 1 minus 0.18 divided by 256. We end up with 0.024. So that would be our standard error. Next, we find the z-score. Remember, the z-score is equal to p hat minus p divided by the sigma. So what do we get? This is going to be, so what was our p hat? Let's come back up here because I already forgot. P hat was 0.223. So we get 0.223 minus 0.18. Divide that whole thing by 256. And we get a really tiny number. So our calculator says the following, okay? It says 1 point, let me write it this way, 1.7, it says e minus 4. So guys, what e minus 4 means, remember this is scientific notation, it actually means that we move the decimal point back 4 spaces. 1, 2, 3, 4. So really what this is 0.00017. Okay? That's a very tiny number for the z-score. Okay? Okay, I'm going to go ahead and do the z-score now. Remember, the z-score is equal to p hat minus p divided by sigma, right? So this is equal to 0. What was our p hat? It was 0.223, right? So 0.223 minus 0.18. And then we're going to divide that by the standard error, which is 0.024. So let me go ahead and do that in my calculator. So when I divide that, I end up with 1.79. Okay, 1.79. By the way, is this a right-tailed or a left-tailed test? We probably should have said that here. This is a right-tailed because of this symbol right here. Okay, we have a greater than symbol there. This is a right-tailed test. And so if I were to draw a little normal chart so you could see it, right? If this is 1 and 2 standard deviations, then that means that what we're doing is we're trying to find the area between 1 and 2, something like that, right? This would be 1.79. Right? Because if this is 0, 1, and 2, then 1.79 would be kind of closer to 2. I guess I kind of didn't draw it far enough to the right, but that's what we get. So we're ready for the actual p-value. And remember, we find the p-value by doing normal CDF. So this is going to be normal CDF. And we're going to do the left z-score, which is 1.79, and the right z-score, which is 1E99. And what does this equal? For this, I'm going to cut to the calculator so you guys can see what it is. So let's go over to the calculator. Again, we're going to do second DISTR distribution. Go to normal CDF, hit enter. The lower limit here is 1.79. The upper limit is still 1E99. Go down to paste. and then hit enter again. So we get 0.037 if we were to round it to 3 decimal places. So we get 0.037, rounding it to 3 decimal places. So we need to state a conclusion, but before I do that, I just want to compare this to alpha, because remember, we're not going to be able to reach a conclusion unless we decide if this is small enough p-value to be statistically significant. So let's remember what the significance level was. It says at 5% significance, right? The problem was. So is this number bigger or smaller than 5%? Remember, 5% is 0.05, and this one is 0.03 something, so this is smaller than 0.05. You got to be really careful when you compare decimals, okay? So what does this mean? It means that this is statistically significant. So we reject the null hypothesis and accept the alternative. However, I want to write this now as a full statement in context, okay? So how do I do that? Remember, we always start by talking about the significance level. So at a 5% significance level, the evidence supports the claim that, remember what we're showing here, the alternative hypothesis is that the proportion of men who were opposed to allowing women to serve in combat positions was higher than 0.18, right? So the proportion of men in the U.S. who, it's disapproved, right? Is that what it says? Who were opposed. Let me just use the exact same language they did. Who were opposed to women serving in the armed forces is greater than 0.18. Okay, so again, let's read that again. It says, at a 5% significance level, the evidence supports the claim that the proportion of men in the U.S. who were opposed to women serving in the armed forces is greater than 0.18. Recall the different errors that we can make in a hypothesis test. When we reject a null hypothesis that is actually true, we make a type 1 error. When we fail to reject a null hypothesis and the alternative hypothesis is true, we make a type 2 error. These errors do not happen because we make a mistake. They happen due to sampling variability, right? This means that you get a sample and you got unlucky with your sample. It contains a misrepresentative amount of successes that does not represent the true amount. So continuing with the example of the 2013 change in U.S. policy on women in combat positions, it is possible that the decision you made in the hypothesis test above is incorrect. Identify the type of error, type 1 or 2, that was possible, and what must be true about the population if this error occurred. So it's possible that we made a mistake. And remember, we rejected the null, didn't we? So that means we may have made a type 1 error. A type 1 error is possible. This means we reject that the proportion of men in the U.S. who were opposed to women serving in combat positions is 0.18. So we reject that even though it is true. Okay, so that is what a type 1 error would be. We could not have made a type 2 error because a type 2 error starts with failing to reject the null, and we never did that in this problem, okay? So this could be a type 1 error, not a type 2 error. Okay, next steps. Generalizing results. Even when a study is done properly, it is important to be careful about how we generalize its results to larger groups. Statistical results should only be generalized to populations that our samples represent well. So, when Gallup researchers conducted their survey on women in combat, they found that about 20% of U.S. adults were against the Defense Department's new policy allowing women to serve in combat positions. In the article cited above, Gallup describes the organization's sampling process as follows. Interviews are conducted with respondents on landline telephones and cellular phones, with interviews conducted in Spanish for respondents who are primarily Spanish-speaking. Each sample of national adults includes a minimum quota. A quota is a required amount of 50% cell phone respondents and 50% landline respondents, with additional minimum quotas by region. Let's move on here. It says about 94% of U.S. adults are able to speak English or Spanish. Based on the description of the study, is the sample representative of all adults in the U.S.? Explain your answer. Well, 94% is close to all, but it's not all, is it? So, no. The sample is representative to only English and Spanish speakers. In the U.S. with phones. That's another important distinction, right? They only sampled people on the telephone. So I know there's not many people out there that don't have telephones, but, there are some. Also, this is something I want to point out here as well, that, requiring 50% landline respondents is a little weird given that most people have cell phones and don't even have a landline anymore. So I would say maybe you're getting a skewed sample here. Maybe older people tend to have landlines. So that's just another thought, okay? So to what population can we reliably generalize the results of the study? Well, let me say it's pretty much the same answer as above. So we can generalize to English and Spanish speakers in the U.S. with phones. Okay? Because nobody else is getting talked to, right? Gallup's study suggests that while around 20% of those surveyed opposed the policy allowing women to serve in combat positions, 74% favored it. Do these results suggest that most people around the world would have supported women being allowed in frontline combat? The key to this question here is around the world. We cannot say anything about how people feel around the world if we only talk about or if we only sample people in the US, right? So let me say no, since the study was conducted only with Americans. We gain no information about how people feel around the world. I bet there are some countries that, feel similarly to the US, but there's probably other countries where they don't, right? Women have very different rights in different countries. So it's very important not to generalize that just because people in our country feel a certain way that we can say that people in another country do too. So the key of this is what we just said here. You need to know statistical inference should never be generalized to a population that is not represented by the sample being used. Very important principle in statistics. Next steps. Statistical versus practical or real-world significance. When we reject a null hypothesis and support its alternative, we're doing so because our sample data are statistically significant. This means that, under the assumption of the null hypothesis, what was observed in the sample was unlikely to occur by chance, as measured by the p-value. Okay, but be careful though. Even when a sample yields statistically significant results, they may not be significant in any practical or real-world sense. That is, even if there is a difference, it may not be large enough to matter. I'll give you an example, right? Let's say that you got a raise at your job. Let's say they were paying you $20 an hour, and then they decided that they were going to raise you to $20.25 an hour. Yes, they did give you a raise, okay? But is it significant? 25 cents an hour maybe is not enough for you to consider it a significant raise, right? So this is what we mean by is it significant in the real world. Maybe the statement is technically true, but it's barely true. Like if you say more than 18%, maybe it's just barely higher, not even a percent higher, and so it doesn't even really matter in the real world. Okay, so we're going to do some examples here. In the previous lesson, we tested the claim that the proportion of U.S. adults who were overweight in 2012 was different from the 36% rate observed the year before. Our analysis used a huge random sample of 350,000 adults that included 126,350 people who were overweight. The sample proportion was p hat equals 0.361, so 36.1% of the adults in the sample were overweight. This is different from 36%, but with a p-value of about 0.22 from a test statistic of 1.23, the difference is not statistically significant. Okay? However, what if we had observed the same difference p hat equals 0.361 versus p equals 0.36 from a sample of 1 million adults. The null hypothesis is p is equal to 0.36, and the alternative is p is not equal to 0.36. Compute the mean and standard error of the underlying sampling distribution, assuming the null hypothesis is true for this revised hypothesis test. By the way, guys, I'm going to take a little break here to say that the code word for this lesson is overweight. Okay? Overweight. So please remember that that is the code word for getting credit for this lesson. So let's move on. So we need to compute the mean and standard error of the underlying sampling distribution, assuming the null hypothesis is true for this revised hypothesis test. Well, what is p in this example? P is 0.36, and the alternative is, that p is 0.36, and then we want to find the standard error. So this is going to be the square root of 0.36 times 1 minus 0.36 divided by n, but now we're assuming that we're sampling 1 million adults. 1, 0, 0, 0, 0, 0, 0. So what would our sigma be? 0.36, 1 minus 0.36, divided by 1, 0, 0, 0, 0, 0, 0. When I hit enter on my calculator, I get 4.8 e minus 4, which is the same as 0, 0, 0, 48. Okay, so that's what that means. Now we need to find the test statistic for the revised hypothesis test. So p hat, remember the problem is asking us to assume that p hat is 0.361 minus the p is 0.36, and we're dividing that by 0.00048. So if we put that in our calculator, we actually end up with 2.08 if I round it to 2 decimal places. So now we're going to figure out the p-value. What would the p-value be? Well, they are telling us that p is not equal, so this is two-tailed, isn't it? So I know that I'm going to do 2 times normal CDF. I'm going to do the right tail, okay? Remember, we're doing 2.08 as our z-value. That means I've got stuff over there and I've got stuff over here. This is why I'm going to double it. So it's going to be 2.08 is the lower limit, and then 1E99 is the upper limit. Let me cut to the calculator so that I can figure out what that area is. So we go over to the calculator. Remember, it's a two-tailed test, so I'm going to do 2 times, and then second, DISTR, go to normal CDF, and the lower limit is 2.08, and the upper limit is 1E99. So I'm going to paste, hit enter, and I end up with 0.038 if we round it to 3 decimal places. So the calculator gave us 0.038. So what happened? You notice that because we changed the sample to 1 million right? Huge sample size. It made our p-value smaller, didn't it? Notice it was 0.22 before, but now it's 0.038. So let's write that down. The z-score, also the z-score got bigger, didn't it? Because look, the z-score is 2.08, and before it was 1.23, right? Okay, so the z-score got larger, and the p-value got smaller. Okay, so is the sample proportion statistically significant with this new sample size using a 5% significance level? The answer is yes, right? Because 0.038 is smaller than 0.05. So yes, it is significant. Now, what is the point of this question? Okay, so this part that we're about to answer is going to illustrate why we're doing this question. So in one scenario above, the increase from 36% to 36.1% is statistically significant, but in another, it is not. Clearly, statistical significance is different from the sort of significance we assign to events through our own values. Do you feel that this increase in the rate of overweight adults in the US is significant in a real-world sense? So this is sort of a judgment call, right? Because if you go up from 36% to 36.1%, does it actually matter is what they're saying. Like, is that big enough that we should be worried? And this will depend on who you talk to, right? So this is a judgment call. So in my opinion, 0.1% increase is small enough that perhaps it is not significant in the real world. Now understand the difference, right? The difference between statistically significant and significant in the real world is the following. Yes, this is statistically significant, but all that means is that the change is real. It really did happen. However, real world significance, the thing is this is a very tiny change, and so the only reason the statistics even captured it is because of the sample size was 1 million, which is huge. So this is a judgment call, though. If you think it's not that it is significant in the real world, then you can put that answer here too. This is really not up to me to decide for you. Okay? So you need to know, with very large samples, even extremely small differences can be statistically significant. With this in mind, remember that statistical significance is different from real-world significance. Statistical significance is measured with probability. Okay? Real-world significance is measured through our system of personal values and is therefore difficult to measure. Let's look at 5. At a busy intersection with no crosswalk, many pedestrians cross the street every day. The fatality rate at this intersection is slightly higher than the national rate. Testing the hypothesis that the rate at this intersection is higher than the national rate yields a p-value of 0.06. Now, is this higher fatality rate significant in a real-world sense? I would say that this, anytime someone asks you for a real-world sense, they ask you, this is a personal choice thing. I would say yes, since any lives lost is significant. However, someone else might disagree. They might say, well, because barely more people are dying at this intersection than at others, we're not gonna worry too much about it. Okay, so it just depends on who you talk to. Given that the increased fatality rate at the busy intersection is only slightly significant statistically, should crosswalks and pedestrian walk lights be installed, though quite expensive? Now, what do they mean by slightly significant? And that comes from this, right? We had a p-value of 0.06, which actually is not considered significant if we look at 5% as the cutoff. If we looked at 10% as the cutoff, then this would be significant, but you could see that it's kind of weak, right? As soon as you get above 5%, it's kind of weak. What that means is that, we're not sure if we made an error here or not. So I would say it depends on how expensive, right? It depends on the expense. But perhaps it is worth it. Notice I'm being a little vague here, and that's because it's really hard to answer this question, right? You don't want to be responsible for lives lost, so a lot of times you will end up spending more money just to make sure that you cover your bases in case, people do die there. You don't want that to happen. Okay. Let's do another example. This will be our last one. Researchers conducted a study to learn whether a new anti-inflammatory medication reduces fever on average for patients with the flu. A large sample was gathered, and the results of the study showed that after taking the new medication, mean body temperature in patients was reduced by 0.2 degrees Fahrenheit. This drop in average temperature was statistically significant, as demonstrated by a p-value of 0.002. People with the flu often have body temperatures that are 2 or 3 degrees higher than normal body temperature, which is 98.6 degrees Fahrenheit. Is the decrease in body temperature after taking to this medication significant in a real-world sense? So the key here is that it only reduced by 0.2 degrees Fahrenheit. Now, what about this really low p-value? Because we know that means something is significant, but that just means it's statistically significant. In other words, that really low p-value means this medicine is definitely working. However, it's only working by this much, right? So I would say no, not in the real world, since the decrease in temperature is tiny, right? I mean, it's not going to help you if you're 2 or 3 degrees above your body temperature and you take this pill and it's only going to lower you by 0.2 degrees Fahrenheit, right? You're going to have to take other medicine too. Knowing that there are other medications that reduce body temperatures in patients with high fever, would you consider taking this new anti-inflammatory medication if it was shown to be safe? Well, everybody has their own judgment call here, right? Maybe you want to take this one also, but I would say no, I would take a medication that reduces fever by a larger amount. Okay, so this little piece here was just to sort of teach you the difference between statistical significance and real-world significance. Statistical significance is when you have a small p-value, and that just means that for sure there is a difference, right? The alternative hypothesis is true. But real-world significance is if that change is still really tiny, though, does it really matter? Okay? Thank you very much for watching, everybody. I hope this video was helpful.